Thanks, everyone. I'm glad to be here, to be back here at the PI after it's been a while, but things has really improved so much. So anyway, today I'm going to tell you a little bit about quantum information and particle physics. And by particle physics, I mean four-dimensional physics. Not two-dimensional, not five-dimensional. It's just good old colliding two particles in four dimensions. That's what I mean. Okay. All right. So
there is a remote control for the slides.
There is. Very good. High tech. All right. So what happens when quantum information means particle physics? Basically, this is what happened. We are putting quantum mechanics together with information theory together with relativity. And why is there something to do? Is because from the quantum information side, the QIS concept and tools in the relativist setting is not fully developed yet. Okay, and the traditional QIS people, they look at the 2 qubit coming in, 2 qubit going out. They never have to think about 2 qubit coming in, maybe 3 qubit going out, that kind of things. All right. And on the other hand, on the particle physics side, the information flow in particle collisions is rarely discussed. I've been teaching quantum field theory for almost 20 years. And never once did I mention the word entanglement when I teach a QFT. That tells you that the kind of mindset that we have when we teach quantum field theory is just something that is not in our mindset. So when you put these things together, I will try to convince you that this is an unexplored territory, and there's still a lot of things to think about. Okay, that's the idea. All right, I know probably not everyone is an expert on quantum information, so let me go through some very basic stuff just to put everybody on the same page. So entanglement, it refers to the situation where a measurement on a subsystem would improve our knowledge on the rest of the system, and a quantum state of system is entangled if it cannot be written as a tensor product. It's a subsystem. And it's best to use some example. So consider a system of 2 spin 1 half particles. Okay, if the spin of the 2 particle system is in the up-down state, this is unentangled because this is a tensor product of a spin up for the first particle and spin down for the second particle. But on the other hand, if we have a linear superposition of up-down and down-up, this is an entangled state because measurement of the first spin, okay, will collapse the state either into a spin down for the particle 2 or spin up for the particle 2. So that means, the state of the particle 2 depends on the outcome of the first measurement. This is what it means to say that the system is entangled. And John Wheeler, famously claimed that, all things physical are information theoretic in origin. So, and we've seen tremendous, progress, insight in combining quantum information science with fundamental physics, especially a lot of them coming from the more formal sides of high-energy physics. So today, I'm really trying to keep everybody grounded here. So as I said, even in this setting, there's still a lot of interesting topics to explore. So I'm going to tell you 3 topics at the intersection of quantum information and particle physics today. First is an information theoretic origin of symmetry. The second one is an area law for entanglement entropy in particle scatterings. And the third topic is a quantum computational advantage in fundamental forces. And let me say that each of these topics is at least a 1-hour talk. I have 30 minutes. So obviously, I'm going just to give you a very quick flavor and show you the results. Okay. All right. An information theoretic origin of symmetry. Symmetry, we all know this, it's one of the most powerful fundamental principles in physics. Chen and Yan coined the phrase symmetry dictates interaction. All the fundamental interactions we know of today are coming dictated by symmetry. And even in condensed matter physics, the famous Landau paradigm uses symmetry to classify phases of matter. Okay, so symmetry is also useful in that setting. However, the first time I realized this, the following question, it struck me, that is that, but we never ask what is the origin of symmetry. It's something that kind of fallen out of the sky, or if you like, it's like Forrest Gump says, a box of chocolate, you never know what you get. So someone just handed it to you, okay? And so the question I would like to ask is, can symmetry be the outgrowth of more fundamental principles? And for example, just very concretely, borrowing from the idea of if from qubit, can symmetry come from qubit? Okay, and so today here I'm going to tell you recent efforts to understand the origin of symmetry from the information theoretic perspective, and what we have learned. Let me give a conclusion first. That is extremization, meaning either minimization or maximization of entanglement entropy in particle interactions lead to enhanced symmetries in the dynamics. Okay. And the examples that we have studied include both non-relativistic, such as in low-energy QCD, and fully relativistic systems, such as the two Higgs doublet models. And the observation applies to both spin 1/2 particles, which are qubits, and spin 3/2 particles, which are sort of 4-dimensional qubits. So it goes beyond just the qubit system. All right, let me try this work.
Does it work?
No, it doesn't work. Okay, you lied to me, Carlos. Okay.
It worked for me. I was wondering, you had the
Discrimination. Let's talk to the director about it. Okay. All right. So.
Can I ask a question? So, are you imagining some sort of a landscape in which like everything is possible, and then is that what you mean by extreme?
Can we defer that to end of this talk? Then I'll be very specific what I'm talking about. Okay. No landscape. Okay, let's just tell you that. All right. So let me tell you first that there are two kinds of emergent symmetry in low-energy QCD that are not transparent in QCD Lagrangian. First is so-called the Schrödinger symmetry, or the non-relativistic conformal inverse. This was first discovered in the 70s. Basically, this is the largest symmetry group that is preserved by the Schrödinger equation. Okay, think about that. I never asked this question before until very recently. We learned about Schrödinger equation from undergraduate, but what is the large symmetry group preserved by Schrödinger equation? It's this non-relativistic conformal inverse. And the second type of symmetry in low-energy QCD is Wigner's SU4 spin flavor symmetry. Again, Wigner observed this back in the 30s, way before the discovery of quantum field theory or quarks. That is, he observed that if you put the proton and neutron, which are almost degenerate in mass, and their two spin states into a 4-dimensional vector, then the low-energy nuclear dynamics is invariant under an arbitrary SU4 rotation of this spin and flavor mixture. So that's the name, spin flavor symmetry for protons and neutrons. Okay. So what I'm going to consider is to consider non-relativistic S-wave scattering of a neutron and proton. In fact, I can phrase this question in terms of completely independent of neutron and proton. Just can treat them as two distinguishable qubits, Alice and Bob, if you like. So we are scattering Alice and Bob in the low energy in the S wave. Okay. So and ask the question: what is the S matrix for this low energy scattering of Alice and Bob? Okay. And this is a well-known a statement for distinguishable fermions in the non-relativistic regime at the low energy. The scattering is dominated by S wave, meaning the orbital angular momentum is 0. And so the S matrix can be decomposed into the spin singlet 1s0 and spin triplet 3s1. And therefore, there are two scattering phases, delta 0 and delta 1, respectively. So these are two-channel scattering. There's the total spin 1 and total spin 0. That's the two-channel scattering. They don't talk to each other. And therefore, rotational invariance and unitarity uniquely fix the S matrix to be the scattering in the singlet channel times the spin projector into the 1s0 channel, and the scattering phase in the triplet channel times the spin projector into the 3s1 channel. This is just simple algebra in quantum mechanics. Written everything in terms of these Pauli matrices. Okay. So this is the S matrix. So to translate this into a problem purely in quantum information, what I would like to do is to think of this S matrix as acting on the 2-qubit system. And since S matrix is a unitary operator, that means I can think of the S matrix as a qubit quantum gate in the language of quantum information. And that means that we can categorize the ability of the S matrix to generate entanglement from unentangled initial state. Okay, so if I say it in this way, it's completely independent of proton and neutron. It's just Alice and Bob and simple S matrix in quantum mechanics, and how do we characterize the information theoretic property of the S matrix as a 2-qubit logic gate.
Ian? So
yes.
So what is special about the S matrix compared to any, like, so something about it being an S matrix as opposed to a general unitary?
No, yeah, in this sense, there's nothing special about S matrix. It's just I'm considering this in the concept of scattering problem. And S matrix is the unity operator that takes me from in state to out state. That's all there is.
But the fact that you decomposed it into definite spin scattering channels,
Right.
That's an additional structure.
That's the fact that it's S matrix and there's rotational invariance and so on and so forth. Yes, of course, yeah. That is coming from the particle physics side. Yes. All right, so let me talk very quickly about how to quantify entanglement. People usually use either von Neumann entropy or linear entropy, but for two qubit system, these are all related to each other, And however, what we really would like to understand is that, the ability of a quantum mechanical operator to entangle. That's separate just from talking about entanglement, because entanglement is really a property of the state. But here I'm talking about the ability of the S matrix to generate entanglement. So it's a property of the operator. Okay. So to do that, what people have introduced is the notion of entanglement power, which takes out the dependence on the initial state. That is, you take a unitary operator acts on the product initial state, then you can compute the entanglement of arbitrary product initial state, then you average over this initial state. So that takes out the dependence on the initial state. And what's left, it becomes the ability of a unitary operator to entangle, and for 2 qubits, the average is over the Bloch sphere, if you know what it is. Okay. So this entanglement power becomes a measure of the ability of the operator to generate entanglement on product state. And people define a minimally entangling operator as the operator that has 0 entanglement power. Okay, so that means that an operator has 0 entanglement power if it always takes a product state to another product state.
If you don't have a 2-qubit system, how many different ways are you going to do
Yes, that's a good question. Yes, we can talk offline. Yes, but there's a well-defined answer. Yes. Okay. But the important thing that I want you to take away is that a minimum entangling operator has 0 entanglement power. That means the operator always takes a product state to another product state. Because when you average to 0, that means it's always 0. Okay. All right. So what are the operators that have vanishing entanglement power? For 2 qubit, it turns out the answer is very simple. It's just 1, which is identity, and swap, which interchanges the 2 qubit. And in fact, you can think of the swap as -1 because swap squared gives you 1. So moreover, in terms of Pauli matrices, we can write the swap as 1 plus sigma dot sigma. This is a useful identity. Why is that? Because I'm going to use this identity to rewrite the S matrix in terms of 1s swap. Because I told you the S matrix is just the spin projected into 1s0 and spin projected into 3s1. So let me use this identity to rewrite the S matrix in terms of 1s swap. Turns out the answer is very simple. This becomes the S matrix becomes linear combination of 1s swap. And since I told you that the only 2 possibility to suppress entanglement is either 1 or swap, this allows us to read off the conditions for which the S matrix would suppress entanglement. For example, if we want the S matrix to be identity, the coefficient of swap must be 0. That means delta 1 equals delta 0. And if I want the S matrix to be the swap, that means the coefficient of 1 has to vanish. That means delta 1 and delta 0 differ by pi over 2. And it turns out that when the two phases are the same, this is exactly when the neutron and proton exhibit this SU4 spin flavor symmetry. And when they differ by pi over 2, this is exactly when the neutron-proton system exhibit the Schrodinger symmetry. And this is the observation that was first made by the Seattle group in the context of effective field theory. That means they write down the effective Lagrangian for neutron-proton scattering in the low energy. There are two operators, CS and CT. You can rewrite them in terms of C0 and C1, and then they computed the entanglement power as a function of C0 and C1. So the blue band are where the entanglement power vanishes, and the white lines, diagonal line, is exactly where you would have a SU4 spin flavor symmetry, and the off-diagonal point are the two places where you have the Schrodinger symmetry.
So in the previous slide, you had two arrows pointing this way. Was this an if and only if as well?
Not it. Where? No. In fact, yes. No. Yeah. It goes this way too. Yes.
Yeah. So
yeah. Whenever delta 1 equals delta 0, that's synonymous with SU4 spin flavor in the context of neutron and proton scattering. Yes.
Just synonymous.
Yes. Yes. All right. So since this example, we have observed similar correlations between entanglement minimization and the appearance of enhanced symmetry in several other systems. This includes 2-2 scattering of spin 1/2 octet baryons, okay? And also in 2-2 scattering of spin 3/2 decouplet baryons. And people have also seen this correlation in the exotic mesons, the 4-quark bound state in X3872 and TCC 3875. And also in the 2-2 scattering of Higgs bosons in 2 Higgs doublet models.
Are those field theory computations, or are they like your qubit models like you had on the previous slides?
It's the same. You can go from one to the other. In fact, that's how we identify the symmetry, because the one advantage about EFT approach is that you can see the symmetry easily.
But I wouldn't know, for example, like what the bipartite system is. Like I might think soft and hard physics is a natural bipartite. Like
okay, this is a linear order QFT calculation, 3 level. Okay. And in fact, there is also an example of entanglement maximization and enhanced symmetry. And I think Carlos talked about it on Tuesday. Okay. So I hope it's clear that we're in pursuit of a new paradigm. Can symmetry be the outgrowth of more fundamental principles? And I'll be the first one to admit that the data points are very suggestive, but we don't yet have a precise statement on what the new principle is. Okay, something is out there, but we don't know what it is yet. And moreover, one important question I think is that can spontaneously broken symmetry be understood in a similar fashion? That is, can we classify phases of matter from the information theoretic perspective? Okay. How much time do I have?
You have another almost 10 minutes.
Okay, then maybe if I have to, I can skip one of the topics. I don't have to finish. All right, so the next topic is an area law for entanglement entropy in particle scatterings. So what we are doing here is that in this case, we are interested in the quantum correlations, meaning as characterized by entanglement entropy in 2-2 scattering of distinguishable particles in the S matrix formula. That is, we are looking at the elastic scattering of AB going to AB. Okay? And then, in the S matrix, the way we compute this is that, S matrix relate in state to out state. We write the S matrix as 1, which is nothing happens, plus IT, which is the transition matrix. And the matrix element of the transition matrix is related to the scattering amplitude that we compute using Feynman rules in QFT. And so we are going to construct the bipartite system along particle A and particle B. Okay, so when we compute the entanglement entropy, we're going to trace over, say, particle A. So that gives us the quantum correlation between particle A and particle B. And I just want to mention that within the particle A, the system is further decomposed into a kinematic part and the flavor part. And kinematic part is a continuous quantum number such as the momentum. And whereas the flavor is anything that is discrete, that could be spin or any internal flavor.
wouldn't you think depending that the whole point of you getting extra symmetry is because of like the
Sorry, this has nothing to do with this. Is a
splitting? It's probably because of the splitting, right?
Okay, in this topic, I'm not even going to talk about symmetry. But this is I'm saying that this is one particular way to construct bipartite system. There are different ways to construct the bipartite system, which we discussed in the paper, but I'm not going to discuss it here.
If I pick different bipartites, then this entropy maximization is going to select for different things. So in this case, it might be a symmetry, and in the other case, it might not be. Or I would assume.
Again, in this topic, I'm not going to talk about symmetry, but I think your question is related to the previous part. In that context, yes, that's a very good question. Okay, so for now, we will assume that pure initial state and no entanglement between the incoming momentum, because that's how we perform the scattering experiment, and no entanglement between momentum and flavor quantum number. That's also how we prepare our initial state in colliders. And but we do allow possible entanglement among the flavors. Okay. And so one thing notice that in QFT textbook, when we do this calculation, we always employ momentum eigenstate for the incoming particle. That means we assume the incoming particle are in exact momentum eigenstate, which normalize to a delta function. That's a problem. Why? Because when you construct the density matrix using the momentum eigenstate, it doesn't trace out to 1. Instead, it traces out to an infinity, which is delta 0. And the source of these infinities come from the fact that we have an infinite system. So one way to regularize the infinity is to put the QFT in a box, introduce a finite volume regularization. Then this delta 3 of 0 becomes just volume. But that's not what we are going to do here. Okay. In fact, we're going to use a regularization that is much closer to the way we prepare the initial state in particle accelerator. That is to use wave packet. Okay. So once we introduce the wave packet, you see that the in state could normalize to 1, and then the initial density matrix could trace out to 1. Okay. So wave packet is the way to go, except that we have to set it up very carefully. Okay. In particular, we are going to take what we call the finite plane wave limit for wave packet. That means, first of all, in the momentum space, of course, we assume the wave packet is localized about a definitive momentum. Okay. And then, however, in the strict limit of a momentum, I can say the position wave function is a plane wave with infinite extent. That means we don't know where the particle is in the momentum space, in the position space. And that clearly is not how we do prepare the initial state collision in the accelerator. So instead, we would take a finite plane wave limit where the transverse dimension of the wave packet is much larger than the longitudinal direction. So just give you a picture. So this is the picture we have in position space for the wave packet. It's kind of like a pancake-like object in the longitudinal direction, whereas in the transverse direction is characterized by this length scale L. Okay, and the reason the physical picture for this is really, when a particle is in the ultra-relativistic regime, the longitudinal direction is Lorentz contracted. That's why you have this pancake-like picture for the wave packet in the high energy. So in the finite plane wave limit is to take the limit that k is the momentum where the wave packet is localized. The width of the wave packet in the momentum space is delta p. So the finite plane wave limit is delta p over k goes to 0. That means the width goes to 0 compared to the magnitude of the momentum. Moreover, we also want a squash pancake. That means delta p times L is much larger than 1. So the transverse size of the wave packet is much larger than the longitudinal side. So after setting up this wave packet formula to compute everything to denote in delta p over k, I'm just going to give you a result because again, I've been teaching QFT for 20 years, but this is the first time I learned how to do an actual calculation of cross-section using wave packet. Okay, so after expanding around the finite plane wave limit, it turns out that this matrix element, which is really the probability for elastic scattering, turns out to have a very simple expression which is just the elastic cross-section divided by L squared, which is the transverse size of the wave packet. Okay? It's a very simple result, and it took a while to understand it. It turns out that there is a very simple way to understand this result by going back to Peskin. This is literally a copy from Peskin and Shorter. The Peskin and Shorter define the cross-section for two bunches colliding with each other as the number of scattering events divided by rho A, the density of a particle A, times length A, what the A is the length of this particle bunch for A, times rho B is the particle density of particle B, times LB, the length of the particle bunch. A is precisely the cross-sectional area of this wave packet. So now we are scattering two particles. So that means rho A times LA times A, which the number of particles in this bunch is 1. Rho B times LB times A is also 1. And A here is precisely the cross-sectional area of the wave packet. And the number of scattering events is exactly the probability of the scattering events. So when you plug this in, you get exactly this expression that the probability for the elastic scattering is given by the cross-section for elastic scattering divided by the transverse size of the wave packet. And then we can use the same, use this result to compute that it turns out the entanglement entropy between particle A and particle B, okay, after you set it up this way, is exactly the sigma elastic cross-section divided by the transverse size of the wave packet. So in plain English, this means the entanglement entropy is a cross-section in unit of the transverse size of the wave packet. That's the plain English. Okay, so a few comments. First of all, just trying to understand this result. Good. So first of all, to create quantum correlation in the final state particle, we need some dynamics. We need something to happen. So that means, you know, the quantum correlation must be given by the probability of some non-trivial dynamics. Okay. And the physical observable characterizing the probability of something happens is exactly the cross-section. Okay? So what is non-trivial in our derivation is that, so the fact that the entanglement entropy is related to cross-section is not surprising. The surprising part is that it's a linear relation, okay, in unit of the L squared. And because dimensional analysis only tells you that, you know, the entanglement entropy should be given by cross-section divided by L squared, but it doesn't tell you that it's a linear relation. That's the surprising part.
So your area law is what exactly?
Come in here. Okay? So the cross-section actually has dual interpretations in physics. First of all, it's an effective area characterizing the strength of the interaction when two particles collide. We are all seeing this classical mechanics calculation of a particle hitting a hard sphere, and the cross-section is precisely pi r squared. That's the area, cross-sectional area of this hard sphere. And then quantum mechanically, it's a probability measure of a specific process to take place. So in this sense, it's an area law.
Now, one thing that's confusing me is, like, I like that if I understood where gravity is coming, because when people talk about area laws in it from Cuban, they really have like you can imagine. Yeah. Sorry. Oh, sorry.
Yeah. Yes.
Basically, like the fact that I might be able to be limited with like how much entropy I can have in a given region is an area law.
Good. So exactly. So what you're saying that in all the other area laws we've seen, there's usually a well-defined boundary where I can talk about what the area coming from. But in this case, that's why to me it's very surprising, because in this case it's only two particles scattering a priori. I don't know where to define a boundary. Except that in hindsight, it seems that cross-section is the only area that we can get out of these two particle scattering.
I think I'm fine with the notion that there's like a target whose area, effective target in this 2 to 2 elastic.
Can you give me one more slide? Okay, because I actually have a comment on that. So then, you know, it's also natural to wonder if other area laws can be interpreted as some sort of scattering cross-section. Of course, the most famous example Its black hole entropy is the area of horizon divided by 4 times G Newton. If I write this horizon as 4 pi r square, and I write G Newton as the Planck length square, you see that actually this 4 cancel this 4 in the 4 pi r. This becomes a pi r square over a Planck length square. It is also a cross section of the black hole divided by some kind of Planck length square. So the question, here is just very speculative. The question is there a calculation one can do to actually flash out this interpretation?
Sure, I think the picture you have is you have like some packets that are interacting in some region of certain size. Now,
Yes.
I think that from the interqubit side, you would expect like a bound on like a Bekenstein bound or something on the amount of entropy you can put there. But the confusion with me is your cross section is like there's no gravity in there, so it's more like
Sure, I'm just as confused as you are, to be honest. Okay, these are all excellent questions. All right, so let me finish up. So one more interesting observation is that now that we related the entanglement entropy to elastic cross-section, it turns out that the total elastic cross-section are known to increase with respect to energy. This is the data from particle data book. You see that this is the cross-section area, total cross-section ranging from 10 GeV to 100 GeV. 5, okay, TeV. No, there is no way.
100 TeV.
How do they make a 100 TeV collision?
I don't know.
Okay, all right. Anyway, so you see that this line is a total. This is the PDG. We should ask PDG. So this is the total cross section. This is the inelastic cross section. This is the elastic cross section. Okay. Moreover, Farsad and Martin showed that there is a universal bound on the total cross section. That the growth of the total cross section is limited by some power of log to the center mass energy. So remember,
Cosmic rays, yes.
cosmic ray. Okay, remember that we teach our students in thermodynamics. If you have entropy and you have energy, you can define a temperature. So the question is, is there some kind of thermodynamic laws in particle scattering? Okay, so again, open question. So given the time, I'll stop here. Yeah, I just don't have time for this. But anyway.
Okay, we have one team set up. We have Maxime.
All right. So let me take this as you, for example, that you showed, right? And they take this idea that the symmetry comes from the maximization or extremization of the entanglement and so on. And I would say that, the mass of, I would conclude from that the mass of up work should be equal to the mass of the down work, and the electromagnetic coupling constant should go to 0, because only in that limit would you have an exact achieved force symmetry. Or do I miss something? I mean, like, I would literally take.
I think
Sometimes in the talks is that we will take this as a principle about the coupling constant, masses, whatever, in our theory.
I think your question is really not about this. Your question is really why don't we see exact global symmetry in nature?
Right. Okay.
It's just approximate. So it could be just everything just approximate. Yes.
Okay, well,
Yeah.
team is ready to go. One more question. I'm gonna. Yeah. Do you mind if I ask someone else? Yeah.
Sorry, I'm a bit confused about this enhancement symmetry, because the symmetry is the symmetries of the theories, and you only get the enhancement points if you adjust the states, right? The delta 0 equals to delta 1, or the difference equals to.
But that's the point. That the point is, in general, delta 0 and delta 1 are functional momentum.
Yes. Yeah.
So in order for this entanglement suppression to occur, delta 0 equals delta 1 across a wide range of momentum. And that could happen only if there's a symmetry. You could totally have an accident that at the particular momentum scale, 200 MeV delta 0 equals delta 1, and then once you go to 250, it doesn't hold anymore. That's an accident. But if there's a symmetry reason, then delta 0 equals delta P across a range of momentum. That's the difference.
Yeah. So we have.
Sorry,
Let's thank Ian again.
That was it?